Hello, my name is Vahid Asadi, and I'm going to talk about relaxed locally correctable codes with improved parameters. And this presentation is based on joint work with Igor Shinkar. Let's start by reviewing some basics of coding theory, and let's start by defining an error correcting code. An error correcting code is basically a function that maps messages of length k to code words of length n, and it has a rate r and distance delta, where rate r is defined by the fraction of the message length to the code word length, and delta is minimum Hamming distance between all pairs of code words in the code. So ideally, we would like to have rate close to 1, and we would like to have large enough distance such that we would become able to decode noisy words. And how is that helpful? Suppose we have a message M and we want to send this message to one of our friends. We first encode the message using this code and get a code word. Then we send the code word to our friend. And assuming the transmission some noise happens and our friend receives a noisy word. However, if the noisy word has distance less than delta over 2, then our friend is still able to extract the message from it. Now here's a question. What if you're not interested in decoding the entire message at once, but we just want to decode one bit or one symbol of the message? Do we still need to read the entire code word? This question raises the notion of locally decodable codes. A locally decodable code is an error correcting code, and it is guaranteed that if we give it a noisy word that has distance less than tau to an actual code word, and if we give it a coordinate I, then it can decode the ith coordinate of the message with high probability by reading only q locations of the corrupted word. Locally decodable codes have many properties. The good property is that they have many applications. For example, in cryptography, in complexity theory, and in construction of TCPs. The bad thing about them is that the best known constructions have very poor rates. The constructions that we know right now are due to the works of Yekanin and Efremenko, and they have super polynomial block length. And the ugly thing is that there is a huge gap between the best constructions and best lower bounds, where the best lower bounds are due to the works of Katz and Trevisan and Woodruff, where they show that the block length should be at least superlinear. Now, motivated by this gap, Ben Sasson et al. Introduced the notion of relaxed locally decodable codes. And the key idea here is that we are allowing the decoder to say don't know or give up if it detects that the input is noisy. And this RLDCs suffice for many applications. So more formally, an RLDC is basically an error correcting code that admits a relaxed local decoding algorithm with the following properties. If the given word is an code word, it is not noisy, then the decoder always decodes the ith coordinate with probability 1. But if the noise is if the word is noisy and distance between the word and an actual code word is less than tau, then the decoder guarantees that it either outputs the correct bit of the message or just gives up and says don't know with high probability. And the decoder does this by reading only q locations of the corrupted word. So this brings us to the main result of this work. In this work, we showed that for all positive epsilon, there exists an RLDC with block length equal O of k to the power 1 plus epsilon and query complexity of 1 over epsilon. This improves the block length of the original work of Ben Sasson et al., where they constructed an RLDC with block length equal to O of k to the power 1 plus epsilon and query complexity O of 1 over epsilon squared. And this matches to the lower bounds of Katz and Trevisan and Woodruff for LDCs, where they showed a 1 over epsilon query LDC must have block length greater than or equal to k to the power 1 plus c times epsilon for some constant c. And improving this construction will result in showing a separation between LDCs and RLDCs. And we can compare this construction to the lower bound for RLDCs, which is due to the work of Gur and Lachish, where they prove for a 1 over square root epsilon query RLDC, we should have block length greater or equal to k to the power 1 plus epsilon. So let's talk about the construction a little bit. There are two main building blocks in this construction. The first one is Reed-Muller code, and the second one is some proofs that we use throughout the construction. And we have a simplifying assumption. Suppose we want to decode the ith coordinate. We assume that the decoder reads q coordinates of the noisy word, and if it detects that some errors are going on, then it just gives up and says don't know. Otherwise, it outputs the ith bit of the given word. So Reed-Muller code is the main building block in our construction, and they are well-studied error correcting codes in both computer science and information theory, and they're defined as follow. Suppose we have a field f with size n and a number of variables m and a degree bound d. The Reed-Muller code is the evaluation of all invariant polynomials of degree at most d over this hypercube f to the power m. Reed-Muller codes have many applications in theoretical computer science and in information theory. And here we just consider the setting of parameters where the degree bound d is less than n. And it is widely known that in this case, the distance is 1 minus d over n, and the rate is greater than d over mn to the power m. For example, we can think of a field big enough such that size of the field f is greater than 10 times d. So what's special about Reed-Muller codes? There is an important property that we're going to use throughout this work, and that property says that the restriction of Reed-Muller codes to planes and lines are also low-degree polynomials. In other words, they're code words of smaller dimension. So we can use these planes and lines to define some local tests. So let's continue by defining some local tests. Suppose we have a point x0 in the cube f to the power m that we want to decode. We can choose a plane p0 such that x0 is in this plane. Now we check whether this plane is a valid bivariate Reed-Muller code or not. Then we can sample another plane such that p0 and p1, which is our new plane, intersect on a line, okay? And then we run the local test for this new plane. And we can continue this procedure until we reach a uniform plane in the entire space. And because we know that the given word is close to a code word, then it's the case that a uniform plane in the entire cube is almost non-corrupted. So if we start with the noisy like coordinate that we want to decode, we must at least see in one of these planes that something is wrong. So everything looks good. It looks like we have a relaxed local decoding algorithm. However, the query complexity is way too much. In this algorithm, we are reading an entire plane at each step, and each plane has size n squared. And this is not going to give us a constant query algorithm. So the solution to this issue is to use some proofs. And the proofs that we are going to use are PCPP proofs. So let's define them. For a language L and a proximity parameter rho, we can define a Q-query PCPP verifier, which is an algorithm that receives an oracle access to an input X and a proof pi. And it reads Q locations of the input and proof, and it has the following properties. If the input X is in the language L, then there exists a proof pi such that the verifier given x and pi accepts with probability 1. And if the input is far from being in the language, then for any proof, the verifier accepts with tiny probability. But because we want to get unique code words for each message, we need a stronger notion here, and we are going to use the notion of canonical PCPPs. The definition is very close to regular PCPPs with the following differences. Here, we assume that for all x's that are in the language, there exists a unique proof pi such that verifier accepts given the input x and the unique proof phi with probability 1. And the canonical soundness property says that if the input x is far from being in the language, or if the proof is far from being the canonical proof, then the verifier accepts with tiny probability. And by the works of Dinur, Goldrush, and Gur, and Paradise, we know that for all positive rows and every language in P, there exists a CPCPP verifier with query complexity of 1 over row, soundness 1/2, and polynomial length proofs. But there are still a couple of issues that we need to solve. The first one is that although these CPCPPs are good and they're going to help us, but they still require robustness properties. It means that not only we need to show that a plane is not low degree, but we need to make sure that it's far from being low degree. And the other issue is that there are way too many planes in f to the power m, and we can't afford to add a proof for each one of them. Because in that case, the entire block length would be polynomial, not superlinear. And in the next slides, we're going to see how to solve these issues. So let's define some consistency tests. And we're going to define them for planes versus point and plane versus line. So the idea here is that suppose an adversary wants to fool the decoder. One thing that it can do is that it can just flip the only coordinate that we want to decode. And because any plane that contains that point is still close to the original plane, we can't see this error with using these CPCPP proofs because we don't have the soundness guarantee here. So we're going to use this plane versus point test to make sure that a point is consistent with the rest of the plane. What we're going to do is that we are going to repeat the value of that point n squared times and concatenate it to the plane. So we are defining a new language here. The language is Reed-Muller for each plane and point such that the plane is concatenated with a single point repeated n squared times, and we check whether this plane is low degree and whether it's consistent with the point. So in this case, that single point contributes to half of the weight of the entire language. So if an adversary flips just one single point, then the distance would be at least 1/2. Similarly, we can define the plane versus line test. The idea here is that we know that at each step of the algorithm, the planes intersect on lines. So we want to make sure that if one plane is heavily corrupted, then the next plane, which intersects with this plane on a line, sees a reasonable fraction of corruption. And the good news is that lines are good samplers. We know that by this basic lemma, if we have a plane and if we have a subset A with density mu on that plane, then for any line that we randomly choose from that plane, the line sees that subset A with almost a similar density of points. So we define the language very similar to what we saw in the previous slide. We just copy a line n times and concatenate it to the plane. So now this line contributes to half of the weight. All right, so far we have found a solution for the first issue, but we still need to reduce the number of planes that we use. And in general, we need two properties from these planes. First, we want to make sure that the number of planes is not very much. And second, we want to make sure that we uh, mix fast enough in this random walk that we're defining. So to solve this problem, we're going to define the notion of H-planes. Suppose we have a field H, and we let F to be its degree M extension. Now we define H-planes to be a set of the planes that are defined by elements in H to the power M. So suppose we have H1 and H2 in H to the power M and X in F to the power M. Then the corresponding H-plane is defined by set of the points that we can write them as X plus S times H1 plus T times H2, where S and T are coming from F. So how many of these planes do we have? The total number is F to the power M plus 2. And this is much better. But we need to make sure that a random walk on these H-planes converge fast enough. So this claim says that if we continue the random walk for M steps, then a uniform point in the last plane is very close to a uniform in the entire hypercube F to the power M. So it means that we can make sure that after M steps, the last plane is somehow close to a uniform plane in the entire space. And remember that a uniform plane is very, very close to being a non-corrupted plane, because we know that the entire word is close to a code word. So from now on, we just consider H-planes and we concatenate a CPCPP proof for all lines and points in H-planes. And we can view this set of H-planes as a de-randomization of all 2D spaces that we have in this hypercube. So let's see the relaxed local decoding algorithm. First, given a point x0 in f to the power m, the test picks a uniform random H-plane P0 that contains x0. Then the test continues by sampling a random line L1 in P0 and then choosing another H-plane P1 which contains L1. Then the test continues sampling these planes for M steps. And at the end, it checks whether these planes are close to their corresponding languages or low degree by reading the corresponding CPCPP proofs and invoking the verifier. And we have shown in our main theorem that if the given word is close to some code word C, but the point x0 is not equal to the actual point in the code word, then with high probability, either the first plane is far from bivariate Reed-Muller code of with emphasis on this point, or one of the intermediate planes is far from being bivariate Reed-Muller code. And our composition theorem shows that composing the Reed-Muller code with CPCPP proofs will result in an RLDC with the following block length: 2 to the power O of m squared times k to the power 1 plus O of 1 over m, where query complexity is equal to the O of m. And the decoding radius is omega of 1, and relative distance is at least 3/4. So let's conclude this presentation by reviewing some open problems. So in the constant query regime, one open problem is to improve the lower bound for RLDCs, where Gur and Lashish proved that for a Q-query RLDC, we should have block length greater or equal than k to the power 1 plus 1 over q squared. So there is still a tiny gap between this construction and the best known lower bound. And it can be the case that this construction is not optimal, and if there is a better construction than this, then this will result in a separation between LDCs and RLDCs. And if the lower bound is not optimal, then it might be the case that it's possible to construct locally decodable codes with better rate using the ideas from RLDCs. Also, what if you're interested in constructing linear RLDCs? From the lower bound of Gur and Lashish, we know that it's not possible to construct constant query RLDCs with linear block length. So is it possible to construct them by allowing logarithmic number of queries? And in particular, is it possible to construct linear RLDCs from ideas from high-dimensional expanders? That's it, and thank you very much for your attention.